Hello, everyone. Welcome to Modern Optimization Methods. I'm Tina Li. Today, we will introduce the third part of Chapter 2, the optimality conditions. In the previous lecture, we already introduced the first-order necessary condition and the second-order necessary condition. So in this part, we will mainly focus on the second-order sufficient conditions. Okay? So what is second-order sufficient conditions? It is defined by, we assume that we have some conditions. Then we try to derive that X star is a local minimizer. Okay? So this is the sufficient condition means. And the second order actually means that we use the second order information. So we must assume that F has the second order Hessian matrix. Okay, so based on the analysis here, so we state our second order theorem like this. So we assume that the Hessian matrix or the Hessian function is continuous in an open neighborhood of X star. And also we assume that the gradient of F is 0 at X star. In this case, then we further assume that the Hessian matrix of F at X star is positive definite. Okay, so it is positive definite, not semi-definite. In this case, we can get that X star is a strict local minimizer. All right, so this is the second order sufficient condition. So you can see that the condition or the assumption are actually somehow the reverse of second order necessary condition. Okay, so we got gradient 0 and the Hessian matrix at X star to be positive definite. Then the conclusion is that X star is a strict local minimizer. Okay? So from this point of view, let's still take an example to show this. All right? So we still take the quadratic function as an example. And if this X star satisfies the gradient to be 0 and also the Hessian matrix, which is a constant matrix, to be positive definite, in this case, we can conclude that X star is a strict local minimizer. All right? So this is an example to show the second order sufficient condition. Now, to prove the result, we still need some techniques. So the technique is the same as before. We use the assumption that Hessian matrix is continuous in an open neighborhood of X star. Then in this case, we can have the Hessian matrix of X star to be positive definite. So this is another assumption. With the two assumptions here, that we can move this X star a little bit in its neighborhood. Then we define this neighborhood as capital D, okay, with radius R. So within this neighborhood, we still have that this Hessian matrix of F at this neighborhood to be positive definite. Therefore, we have that if we do Taylor's expansion of function F at X star plus P, then we can have the three terms here, okay? Here we expand it to the second order information, all right? So the first order information, the second order information, and the second order information we got a Z. Z is between point X star and X star plus P, okay? Notice that this P, we choose its radius smaller than R. So X star plus P is within this neighborhood, capital D. Therefore, the point Z is still within this neighborhood. by the assumption here, we have that the Hessian function of f at z is strictly or is positive definite, implying that the second term is strictly greater than 0. Alright? So in this case, it means that this function value is greater than function value of f at x star. Alright? In other words, we have found a neighborhood of x star. Within this neighborhood, any points have strictly greater function values than fx star. Alright? So in other words, x star is a strict local minimizer. So from this way, we have showed the second order sufficient condition. So different from other two theorems in the previous lecture, in this proof, we didn't use the contradiction way. Alright? Okay, so this is another way to prove the theorem. Now, we have several remarks in terms of second order sufficient condition. So the first one is that the sufficient condition are those conditions under which we can guarantee to find a local minimizer. Okay? So there may be different types of second order sufficient condition. As long as it involves second order information and it can lead to a local minimizer, it will be called a second order sufficient condition. So here in the theorems, we only introduce one way of second order sufficient conditions. There may be others. In other words, if some second order sufficient condition fails, it does not imply that this x is not a local minimizer, because there may be some other ways to check or to prove that whether this x is a strict local minimizer. Okay? So the second remark is that here, the second order sufficient condition we present is actually stronger than the necessary conditions. Okay? So recall that in second order necessary conditions, the condition is that f, the Hessian matrix of f at x star is positive definite, semi-definite. Okay? So this is in the second order necessary condition. However, in the second order sufficient condition, it is actually the Hessian matrix of f at x star is positive definite. Okay? So it's different. In second order sufficient condition, the condition is much stronger than the second order necessary condition. Alright? And also the result is that it guarantees a strict local minimizer. Alright? So it is a strong local minimizer rather than a weak local minimizer. Okay? So the conclusion is also different. Now, the final remark is that the second order sufficient condition are not necessarily for a point to be a strict local minimizer. There may be others conditions. Alright? I'll give an example here. For example, you got x power 4, this function, and obviously 0 is a local minimizer. Alright? And also it is a strict local minimizer actually. However, as we can verify that the Hessian matrix of f at x star is actually 0. Okay? So in other words, the second order sufficient condition does not hold. However, x equals 0 is also a strict local minimizer. Alright? So it means that even second order sufficient condition fails, x star may also be a strict local minimizer. Alright? So these are some remarks about second order sufficient conditions. Now, let's take a look at convex case. So for convex case, we have some very special results, actually very beautiful results. Okay, so the first one is that if this function is convex, we can know that any local minimizer is also a global minimizer. Okay, so this is a beautiful result because in this case, you do not have to worry about local or global. Both of them, they are global minimizers, all right? And the second result is that if f is differentiable, then any stationary point x star is actually a global minimizer of function f. Okay, so this is the second result. Now I still put a quadratic function here to show you that in the convex function case, x equals 2 is both the local and the global minimizer. All right? Now, let's try to prove the result. Okay? So for the first part, we still use the way of contradiction. We assume that x star is a local minimizer, but it is not a global minimizer. All right? So in this case, we still try to derive some contradiction. And how we derive the contradiction? We must use the convexity. Okay, so it is a very important property. So to use the convexity, because x star is just a local minimizer, so there must exist another point whose function value is strictly lower than function value at x star. So we denote it as point z, and fz is strictly smaller than fx star. In this case, we draw a connection between z and x. Okay, so we draw a line segment between x star and z. All right. In other words, we take a convex combination between the 2 points. We denote the convex combination as x. Now we consider the function value of f at x. Okay, so by the convexity of f, we know that the function of f at x must be smaller than the convex combination of the 2 function values. In other words, we have this condition here. Okay, so this is by the result of convexity. Moreover, we have assumed that the function value of f at z is strictly smaller than fx star. Therefore, we get that fx, the function value along this line segment, is strictly smaller than fx star. All right? In other words, in a neighborhood of x star, we have found a piece of the line segment whose function values is strictly smaller than fx star. Okay? In other words, x star is not a local minimizer in this case. Therefore, by this way, we have derived a contradiction. Therefore, we can see that if x star is a local minimizer, then it must be a global minimizer. Now, this is the first part of the proof. To show the second part of the result, we still use the way of contradiction. However, the proof is much more simpler than the first part. Okay? So the conclusion is that we try to prove any stationary point is a global minimizer of f. So for contradiction, we assume that x star is a stationary point. However, it is not a global minimizer. So similar to the previous one, we can find a point z whose function value is strictly smaller than fx star. Now, we still use the convexity. However, we use the equivalent conditions of convexity. That is the first order conditions for optimality condition. Okay, So in this way, the condition here actually the convexity condition. So we have that function value of f is smaller than function value of fx star. However, by our convexity, we actually know that this must be smaller than 0. Alright? However, since x star is a stationary point here, right? So this must not be 0. In this way, we get a contradiction here. Okay? So by the way of contradiction, we have showed that x star must be a global minimizer. So we finished the second part of this proof. Now, let's make a brief summary about this part. So in this part, we have showed the first order necessary condition, the second order necessary condition, as well as the second order sufficient condition. In particular, we have discussed the convex case, and we have some special and beautiful results. Okay? Now, let's stop here and see you next time.